going to do some more beam deflection today, except this time we're going to develop the equation of the elastic curve ourselves. Last time we used predetermined or pre-derived equations of the elastic curve and special cases where the maximum deflection or the slope at the end of the beam was already given in equation form anyway. And we're going to figure out how did they get those equations. So to do that, we're going to have to take a theoretical approach, do a little bit of calculus, some integrating, use a definition from mathematics, and we can eventually get to how are we going to get the equation of the elastic curve for whatever we might be dealing with. So let's start with something pretty simple and generalize from there. So we've got a simply supported beam. It's got a pin and a roller. We'll put a point load just so it would deflect downwards. Now I'm going to exaggerate the amount of deflection that we're dealing with here a lot. So I'm going to use this circle template to take a look at how this thing would be deflecting. So let's say that, it bends that much, which is totally unrealistic, but will do for what we need. So we're just kind of saying that this beam, we pushed on it and it turned into this shape. Now this is not true. This is definitely exaggerated, but it is not what we're going to derive from this is still valid, even though we exaggerated the amount of deflection here. Now what we did is I took a circle template and described this deflection in terms of the arc of a circle. That part is true. It's just, the diameter of the circle that really describes this deflection is much, much larger than the diameter of the little circle template that I'm using. And there are a couple of terms, variables that we need to define here. And let's take one of them. I marked this as the center point. So, this is kind of the arc of a circle, and it has a included angle here of theta. So again, we're going to do this all in variable form, so that theta could be anything. There's also, if we had the original beam somewhere, there's a neutral axis, right? So I'm going to draw this blue line as the neutral axis. So this neutral axis has basically the same length as the beam. Here we have deformed the beam. It's caused it to turn into this curve, and that neutral axis is also curved. I guess I can't really, I'll have to freehand it. So there's the neutral axis in its deformed shape. It has the same length, because remember, the deal with the neutral axis is it is the point where there's no flexural stress. So if there's no flexural stress, then there's no flexural or axial, in this case, strain. If there's no stress, there's no strain. And so this blue line, even though it's curved, it's the same length as it was originally. So that's going to be important later on. I'm going to give this distance here, so the distance from here to our center, I want to make that r. So it's a radius. This is the radius of curvature. Let's write that in black, not green. Now there is a corresponding thing called just curvature. And it equals 1 over the radius of curvature. And the thing why I point this out is because there is a mathematical definition for curvature. And that definition is this. We're not going to derive this definition. We're going to take it as true. So I've got a second order derivative of y with respect to x, and then I'm going to divide that by this denominator, 1 plus dy dx, so the first order derivative, that dy dx is squared, and this entire denominator is raised to the 3/2 power. So this is a mathematical definition for curvature, which is 1 over the radius of curvature. So that's fine. Dy dx here, if I were to take and draw a tangent line at some point, let's draw it to the tangent to the beam. Draw a tangent line to the beam at some point. Dy dx is the slope of this line. Now, I have drawn a very exaggerated amount of deflection here, and in the real world, your beams don't really do this. You know, they don't really bend that much. You might make the beam that shape to begin with, but it doesn't start out this shape and then you load it and it ends up this shape. That's just too much curvature. So in general, this slope is really close to horizontal. You know, if this is your beam, then you know it might have gone from perfectly flat to a little bit, you know, a little bit deformed. I'm doing this, but not much. And so a little bit. So that slope is very small. So if I put a very small number here, square the very small number so it gets even smaller, add it to 1, this term is pretty much 1 point, a bunch of zeros and some numbers. But then I take that 1 and raise it to the 3/2 power, then it gets even closer to 1. So this whole denominator is more or less 1 as long as this curvature, this slope here, is small. And in general, you want the beams that you're designing to not have a lot of curvature to them when they're put into service. So that's for beams in bending. This denominator is more or less 1, which makes 1 over r, that curvature term, pretty much just equal to this, the numerator. So that's good. That helps us a little bit. It doesn't tell us anything about how we relate this to the load or anything like that, or the equation of the elastic curve, but it gets us a bit of information that we can use later. So that's one thing. Now, let's go back over here. So this blue line, that represents the neutral axis, and it has a length, and it's an arc. You know, these were made by circles. And any beam you could describe, no matter how it's bent, you could describe each little piece of the beam as some type of circle. You know, maybe you've got it bent into an S shape or whatever, but there's an arc here and another arc here, another arc, you know, all these little arcs put together. And so this is not unreasonable for what we're thinking about. It is exaggerated, just not, the idea is not unreasonable. The exaggeration is unreasonable. So this length of the neutral axis here is an arc length, r theta. So I'm going to call it we'll call it the blue line right now. But it's the length of the neutral axis through the length of the beam. Length of that blue line is r, well, I used a capital R, didn't I? R times theta. So that's just an arc length, that's all that is. Now let's draw another line on here. Let's make it red so we have a different color. I'm going to offset it from here some amount. And so that line would be down here. Doesn't really matter where I offset it. I could have drawn it above it or below it. Doesn't really matter. But remember, when we're doing our flexural stress equation and we have to define a point that we want to calculate the flexural stress, maybe this is the line that that point is on. It could be at the very bottom of the beam is where I could have put it. I just can't draw on top of that, so I put it in between. Anyway, there's some offset, some tiny little distance between the neutral axis and my red line, this other axis. And I've been using the variable y as that my over I, where y was the distance from the neutral axis to the point that I was interested in. So I can use a y here just to keep consistent with that notation. So here, before I bend it, the blue line and the red line are the same length. They're both however long the beam is. After I bend it, this red line is actually longer. I even had to use a big circle to draw the bottom and a smaller circle to draw the top. They're not the same length anymore. Remember, the neutral axis is the point where on one side you have tension, the fibers are being stretched out. On the other side you have compression, the fibers are being compressed. So this top side of the beam is getting shorter, bottom side is getting longer in this particular orientation for the bending moment. But this red line is now longer than it originally was here. So whenever I lengthen a line or whatever it is, then I have induced some strain in that line. And we have a definition of strain is equal to the change in length divided by the original length. That was axial strain. So if I have this offset y, then this red line has a radius, r plus y. So it has a length now, a final length of r plus y as its radius times theta. So that's its arc length. So that's the current length of the red line, but I want the change in length. So the current length minus the original length. Originally the red line was the same length as the blue line. So the length of the blue line is r theta. And then I divide by the original length. And I've got a lot of similar terms in here, some r's and thetas. Let's go in and take that r plus y and expand it just to make this a little simpler. So I have r theta plus y theta minus r theta divided by r theta. So I've got r theta minus r theta, and I've got y theta over r theta. And the thetas cancel out. And I have y over r equals the strain. These r's are the same. This r is the radius of curvature. This r is the radius of curvature. So now I have a way to link between the mathematics of curvature and the strain in the beam. Now, I've been wanting to deal with the flexural stress in the beam, not the strain in the beam, but we do have a way to relate strain to stress. We haven't used it in a while. It's been several weeks since we've actually used the relationship between stress and strain, but we do have Hooke's law that relates stress through modulus of elasticity to strain. So we have that relationship. So now we can get from mathematics to radius of curvature to strain to stress. And I also have a flexural stress equation, sigma equals negative m times y over I, and there's m, the bending moment in the beam. So that's something that I know describes how this happens. So that bending moment inside the beam tells me something about the shape of how this thing is going to bend. So if I can get bending moment into this equation, into here, into curvature, back to mathematics, I can begin to get down to figuring out how I'm going to create an equation of the elastic curve. So we need a new sheet to put all these combined together. Let's just put this over here. Let's write all our equations down. We have sigma equals negative m times y over I. So that's our flexural stress equation. We have strain equals y over r. That's the one we just got from the red line and blue line. And we have 1 over r is more or less equal to the second order derivative of y with respect to x. So we have all that. And we have Hooke's law. There we go. So let's plug in. Do I want to do this? Let's see. I think it'll be just to make these y's not the same as this, not get confused with this y. I'm going to go and take the worst case scenario over here. And we have done that before. I don't know if you remember or not, but when we did sigma max, we wrote the equation like this: m times c over I, where c is the largest value of y that you could put into the equation. And remember, y is the distance from the neutral axis to some point at the top or the bottom of the beam. And when you put c in there, it's telling you to take the larger of those distances. So we don't have, so basically it's saying that we're at the very bottom of the beam or the very top of the beam, whichever is larger, whichever is further away from the neutral axis. I'm going to do the same thing here with this strain and just put a c in. So the maximum strain is when you put c over r. It doesn't really matter. We could have kept the y's, but they might have gotten a little confusing with the y over here. So I'm going to keep them separate as c's. All right, and I dropped that negative sign off so that we're not so much concerned with is it tension or compression, just is it bending or strain or whatever. We don't really concern ourselves right now if it's a compressive stress or a negative compressive stress, positive tensile stress. All right, so now let's put some of this together. Let's start with our Hooke's law equation. Sigma is m times c over I equals E times epsilon is c over r, right? And if we look at this guy, we've got r in a denominator. If we do, well, look at this, c and c, so it really didn't matter if we had a y or a c or any letter in there, they're going to cancel each other out. As long as we put the same thing in both of these, then they cancel each other out, which we should. If we want the stress at one point, we want the strain to be at that same point. So these should be the same value. They cancel out anyway. If I move this e over, m over e I equals, now I'm left with just 1 over r. 1 over r is this term. So I end up with 1 over r is the second order of derivative y with respect to x equals m over e I. So I've got something here. It's not the equation of the elastic curve, but the equation of the elastic curve is y of x. So if I integrate this once, I will get dy dx, which is the slope. If I integrate the slope, I will get y of x, which is that deflection. So I just had to integrate this thing twice. Now this m is actually, if you remember drawing a shear and bending diagram, or earlier when we drew a beam and cut it open and solved for m is actually a function of x. All throughout this beam, there are different values for the bending moment. So it's as x goes from one end to the other, that bending moment changes. So m is a function of x. So I'm going to write it as m of x. All right, so we just need m of x. So we need to draw us a beam that we want to do some calculating, figure out the equation of the elastic curve for. Let's put that right here, just to keep on our page. I'm going to do a cantilever beam because the point that we're about to do now isn't necessarily the beam, it's the moment as a function of x inside the beam. So I'm going to keep it in variable so that we're not actually solving a very specific one. We are solving the specific case of a cantilever beam, point load on the end of it, and the beam is L units long. So we are, that is a specific case, but we don't have a value for L or P, so we are generalizing a little bit. So this is very much like case 1 in the chart that we used last time, and they had an equation of the elastic curve. Now we're going to do a little bit different because what they did is they had x equals 0 at the wall, and then over here x was equal to L. We're going to start x equals 0 here and x equals L at the wall. So we're just going to make x go the other direction. So we'll end up with a little bit different equation. So it's slightly unique from just looking it up in the book. But what we need to do is we need to cut our beam open. We'll draw this side of the free body diagram. We will take P, whatever value that point load is. We're going to set X starting here, going in this direction. So this is X equals 0. Inside this beam, we have a shear that is a function of X, or it could be, in this case, shear just equals P if we did summation of forces in the Y direction. The shear force doesn't have any bearing on this equation though, so I'm not going to worry with it. Here is M of X. That's the one that we want to put right here and do our integration. So if I solve this free body diagram, do summation of moments about this cut point, we'll do clockwise positive. We have M of X plus P times X equals 0. So therefore, our equation for M of X is equal to negative P times X. That's what we're going to put in here and do our integrating. So that's important. This was important too. Now, I put an equal sign here, but this is an approximation because this is an approximation. But as long as your beam is not really deforming, then it's a good approximation. Let's start a new page because we're not going to have room on this page for all that we need to do. So let's start with this. We'll use the big pen for this one. So I'm just copying down where we left off. The second order derivative, y with respect to x, moment as a function of x, over E, which is the modulus of elasticity, so that shouldn't change. That should be a constant. The beam is the same material from one end to the other, times I, which also shouldn't change. That's the moment of inertia. So the moment of inertia of the beam shouldn't change because the beam's cross-section probably does not change from one end to the other. Let's put in our M of X equation. Negative P times X, EI. And let's integrate. Let's integrate this side, and let's integrate this side. Well, in that one, this is the same thing. With respect to x, this guy, with respect to x, we're doing an indefinite integral. It would be from 0 to L, but right now it's an indefinite integral. So this side is just dy dx, which is just the slope. That is just theta. So that dy dx is, if I can find our first sheet, that's the slope of this tangent line at any point. But it's a function of x now, so we can put it at any point on the beam and get the slope at any point. This integral, e and I are constant, so we can pull those out. And then we just need to integrate negative p x dx. So that's just p x squared over 2. So now we have, I'm going to put theta in here for now. I'm going to go ahead and take these EI and put them with theta. And the integral of this thing the negative sign. I guess I could put the negative over there or leave it over here. I'm going to leave it with this guy. Px squared over 2. We did generate a constant of integration, so plus C1. So we need to solve for that C1. So to do that, we need to go back here and find a boundary condition where we know something about theta to be true. So in our startup diagram here, we do know that this beam, little short beam, but it's going to bend downward if you push P. It's going to bend something like that. But at the wall right here, assuming I could hold it steady enough, that slope is horizontal all the time. No matter what I do here, that slope should be horizontal. So at the wall, theta should equal 0. So this should be equal to 0. So at, now remember for me, the wall is x equals L. In fact, let's, x equals L. At this end, x equals 0. So at x equals L, theta equals 0. The slope is horizontal. So if I plug these values into this equation, I can solve for that constant of integration. So theta equals 0 makes this whole side equal 0. X equals L. Therefore, that's C1. C1 equals, we'll move it to the other side of the equal sign, and it becomes PL squared over 2. All right, so now we can take this PL squared over 2, plug it into this equation. I'm going to change that back to dy over dx because we're going to integrate in a second. And we have EI times theta is dy over dx equals negative px squared over 2 plus c1, which is plus pl squared over 2. All right. If I integrate this one, that dy dx becomes y of x, which is the equation of the elastic curve. So we need to integrate this guy with respect to x. I didn't leave much room for writing dx in there. And this one with respect to x. So this side, e and I are constant, so they just come out of the integral sign. And then the integral of dy dx is y of x. So there's the equation of the elastic curve multiplied times EI right now equals this side, negative px squared over 2 dx is going to be negative px cubed over 6. PL squared over 2 dx is plus PL squared x over 2. I generate another constant of integration, so plus C2. And we have to start a new page. So here, I need to know something about y of x in order to solve for this this constant. So back on our page that had here, I know, again at the wall, at x equals L, that there's no y of x. There's no deflection right there. So right here at the wall, I can push on this, pull it whichever way, but this point does not move up or down. This point does, and all these points in between, but right at the wall, it doesn't move up or down. So I know I have a similar situation where at x equals L, y of x equals 0. So that's a boundary condition that I know. So I've got this whole time, again, y of x equals 0, so this side becomes 0, equals x is L, so negative p L cubed over 6 plus p, this is L squared times L, L cubed over 2 plus C2. So I can solve this for C2, and I get, well, I get a common denominator. This is PL cubed over 6, multiply this guy times 3, PL cubed over 6, 3 PL cubed over 6. and I'll end up with a 1/3 PL cubed, combining these together. And plus C2. So move C2 over to the other side, or move this to the other side, whichever. C2 equals negative PL cubed over 3. So taking that and plugging it back into our equation here, E times I times y of x equals negative px cubed over 6 plus PL squared times x over 2, plus, but it's actually a negative, so negative PL cubed over 3. So there's my first constant, the second constant of integration. There's the original m of x being integrated twice. E times I is constant. I really want y of x by itself. Over here, each one of these terms has p, and then there's a common denominator of 6. So I'm going to take the EI, move it over here, collect the p's, and collect a common denominator of 6. So y of x equals, and I'm going to leave p, I don't want the negative one, so I'm going to put p over E and I get divided through both sides. Common denominator is 6, and then the leftovers here become, this one would just be negative x cubed. This one, I'd have to have a 3 here, so plus 3 L squared x. This one I'd have to multiply times 2, so minus 2 L cubed. So this guy right here, that is the equation of the elastic curve for this beam, starting at x equals 0 at the free end, x equals L at the wall. So that's, in those diagrams last time I was telling you a lot about, you have to follow what they have done to derive that equation. So if they measured from the wall out, then that's what you have to do if you're measuring to put a value for x into your equation of the elastic curve. Since we did this one where x is 0 at the free end and x is L at the wall, then if we use our equation of the elastic curve, we have to put, if we want to know the deflection at this point, then we have to measure from here over to that point. So you do have to know something about the original free body diagram. I guess this isn't this one, free body diagram of how this bending moment was created in order to properly use the equation of the elastic curve. So this equation, if we changed up our beam a little bit, so if we have this, then we're fine, as long as we start at x equals 0 and x equals L at the wall. But if we do this, now that equation is not going to work any longer. You know, if we drew this free body diagram, you know, and drew this, it would look like this guy. M of x would be the same. We would still integrate the negative p times x. We would still technically have our boundary conditions here the same, because at the wall, those things are still true. But once we get into this section, this equation that we just derived wouldn't work because the bending moment changed. So let's cut that guy open. I'm not going to do the whole thing, but let's just see what the bending moment is in this part. So there's the bending moment we want. we have this distance, let's just call it A, the distance between the 2 point loads. We're measuring still from x equals 0 here out to our cut, so that'll be x. So if we do our summation of moments about this point that we, did our imaginary cut for our free body diagram, we get m of x plus P2, that moment arm is x minus a, plus the original P1, I didn't give it a subscript, but 1 times x. So we would need to move equals 0. Move these to the other side of the equal sign, and m of x equals negative px minus p2 times x minus a. That's the thing that we would have to put into here and start the process all over again. And we would get a new equation of the elastic curve. We could use those same boundary conditions again to solve the constants of integration, because they would still be true. There would be no slope, or the slope would be horizontal at the wall, and there'd be no deflection at the wall. But this is what we'd have to integrate. So every time you change something, you add a load, you add a distributed load, you add a concentrated moment, or whatever, so anything that you add that would change this internal bending moment equation, you would need to take into account, and that would be a new section in your beam. So if you were trying to plot the deformed shape or the deflected shape of this beam, you would do it in 2 pieces. You would solve this thing and see what it looks like, and that would give you the deflection from the wall out to this point load, and then you would use this equation to get from the point load out to the rest of the wall. Now, there would be a little bit of an issue. Maybe now that I think about it, you couldn't just use the original. I don't know that you could actually use those original boundary conditions, because those boundaries aren't part of this section. So you'd probably have to do this one first and figure out what the boundary conditions are at this point. There's some deflection amount here. So at x equals a, the deflection is some other than 0 number. So you'd have some number in there. So you wouldn't be this equation exactly, would it? Because this one has these constants of integration with the boundary being over here at the wall. The boundary for this section is actually right here. So you'd have to solve this section first to see what those boundary conditions are, in order to plug them in to solve for the constants of integration and get slightly different numbers over here, because there is some deflection and some slope that it starts at. So it wouldn't be quite as simple as just tacking this on to the end. You'd have to redo this one also. So every section has its own little piece that you would have to deal with. But if that is one way to calculate the deflection, or to plot the shape of the beam from one end to the other, is to do something like this. You could do some more like iterative methods with just you have this bending moment calculated in a bending diagram or something like that. Maybe you could do it that way. But this is how the equation of the elastic curve is derived to use the charts. Now, most of the time, you're just going to use those charts, and you're going to figure out ways to combine them together to create a simple version of this. Like this would be really simple with superposition. It's 2 cantilever beams that you have to add together. One where the point load's at the very end, one where the point load's in the middle, and the rest of the beam just slopes downward. And you just add those together using superposition in case 1 in the charts that we looked at last time. So it's not that you have to develop the equation of elastic curve to do every one of these beams. But it's useful to know, how is it coming? How do you get to this point? Where's it coming from? What are the assumptions that were made to get here? We did this approximation with the radius of curvature, and all of those equations in the book assume this assumption. If you ever do have a large deflection, this begins to break down, and you can't make, let's see if we can find it. There we go. We can't make this nice, neat little assumption. We might have to deal with this. But in the real world with steel beams and beams in buildings and machines, you aren't going to have a large deflection. So you're going to be okay in most cases just using the chart straight out of the book, because you're not planning on much deflection at all. All right, I hope that helps make sense of some of this stuff a little bit, gives you an idea that it's all not just made up equations, that they actually have a root in something theoretical, and it is possible to go through and figure them out on your own if you really need to for some reason. I will see you on Thursday, and on Thursday we have actually, I think we're talking about the next lab, so it's another SolidWorks simulation. We're going to do a 3-point bend simulation in SolidWorks, so it ought to be a relatively short one, but that is what we're doing on Thursday. If you want to follow along, get SolidWorks up and running, and we'll do a little 3-point bend simulation to see how these simulated truss members might behave in